Hey, I almost said good morning, but it just became afternoon a few minutes ago. So good afternoon, everyone, and thank you for joining us. Jay and I have had a lot of fun developing this class, so we're excited to share it with you. And if you're puzzled about the image on the screen, I was drawing an analogy between high performance buildings and high performance vehicles. And the one shown here is the Tesla Roadster. So it is decarbonized, being all electric, and it is high performance. So that's our sort of launch for this and gives some preview of what we'll be covering. So a little bit about me, as little as possible. We got to talk fast. You can sort of read my background, and I will give this over to Jay and let him introduce himself.
I'm Jay Gentry with Passive House, California. I'm on the board there. Vietnam age, so I didn't get to pick whether or not I went in the military. I was in the Air Force for a few years, and I've been a marketing and sales consultant pretty much exclusively for about the last 15 years, working with organizations, companies, people who are interested or working in some way to save the planet, if you will. So happy to be here. It's been a real exciting time putting it together with Ann, and I'm looking forward to going forward. If you advance the slide, please. You see we've got the learning objectives from the AIA, and in general, what I just want to let you know is we have two goals, and that is to make you aware of some things that perhaps you're not already aware of. And most importantly, we've achieved our goal if you at the end have the knowledge to make informed choices about how you can fit in, what you're going to do, how you can take action to help us reduce greenhouse gases and make the planet a safer place for our grandchildren. We have a poll now, so I'll turn it back to Ann.
Okay, and let's see, Ian, are you able to actually implement this? Maybe we didn't warn you.
I don't think so. We'll have to do it through the chat.
Okay, great. So this is fun. We just want to get a general idea of who's in the room, who we're talking to. So yes, if you could in the chat indicate how you would describe yourself relative to this topic, that will give us some insights into. Okay, so we've got an engineer, a public agency, C, public agency, we've got C, great. Oh, we got a bunch here. Lots of public agency folks. All right, B, an architect, engineer, or other, another engineer, another public agency, architect, researcher, education consultant. Javier is Javier. Glad to know that. Architect and builder, architect. Okay, awesome. That's really helpful. It gives us a sense we have a nice smattering across the groups that we expected to see. So that is helpful. So we've broken down the content here into 4 pretty broad topics. These are really just kind of markers to indicate how we progress through the material. First, to talk a little bit about the big why we felt this topic was timely and that we hope it will be helpful for you. Then what we think it means for the building sector, how to implement high performance. And then last, what you can do, and again, looking at that through the lens of your various roles in the industry and occupations. So first of all, the why. The why is we're facing a lot of change. The change is a constant, of course, across our culture, but certainly I feel that we're at a really very significant inflection point, that I've been embedded in the world of green building for inching towards 30 years now, and I have never seen so much change happening so quickly. And it's very exciting, but it's also daunting. And so that's the big why, and a few more specifics about that. Right, you all live in a region that's been hit very hard by fire, as do I. I live in Sonoma County. Although I moved here, I guess, after the worst of the fires, we definitely experienced our share of those issues. And we're understanding that we need to limit the increase in global temperature to 1.5 degrees centigrade in order to really maintain livability on the planet for humans. The cockroaches will survive. We are not so certain, I think, of our future. And then I think at the bottom of the screen, this latest, that just last month, the United Nations warned us that we are on course based on current projected pathways and intentions expressed at COP26 for catastrophic warming. That is 2.7 degrees centigrade, well above the 1.5 that we have been told is the safer and yet still problematic pathway. Now, very quickly, this chart, I don't expect you to read all of the fine print here, but this was published a while ago by the World Resources Institute and shows how the difference between just 1.5 and 2 degrees centigrade makes a tremendous difference in terms of various factors of livability on this planet. So extreme heat will go from affecting 14% of the population at 1.5 degrees up to 37% of the global population at 2 degrees centigrade. We will lose 7% of Earth land where ecosystems shift to a new biome at 1.5 degrees centigrade, 13% at 2 degrees centigrade. So these are just a few statistics that certainly raise the hair on the back of my neck. And I think as much as we may all be aware that climate change is a problem, this chart was very much a wake-up call or a bucket of cold water, choose your metaphor for me, that these are very, very concrete changes that we are facing if we don't act much more quickly and radically than we have to date. And so what this all represents is so many different crises that we are facing. We see sea level rise, flooding from mega storms, obviously wildfire, drought, the increasing heat in the far north, which is very unexpected, and virus, wildfire smoke. And of course, all of these things unequally affect different parts of our population. So those who are most disadvantaged and least able to cope with the problems we face are the ones who face them the most. So we really need to address these. So on the bright side, or on the solution side, I really like this graphic from the Lawrence Berkeley lab. Okay, so how do we get to net zero carbon emissions? Carbon emissions, of course, being one of the biggest drivers for climate change, along with methane too. So of these 8 sort of high level big solutions, 3 of them are very squarely in the world in which we operate. Increasing solar wind capacity, which we do partly on our buildings, not exclusively, of course. Increasing the heat pumps sales share rather than the gas fueled alternatives. That's definitely within our bailiwick. So you're seeing a lot of changes with local jurisdictions about that. And similarly with all new buildings and appliances meeting strict energy efficiency goals, as well as in many cases, electrification. So lots of stuff going on. And then many of these other things touch more or less directly or indirectly in our world of the building industry as well. So zero emission vehicle sales, having EV charging is increasingly an important part of buildings. Carbon sequestration is a topic that comes up in conversations about how we build our buildings. So all of these are relevant. I've just highlighted the 3 that are most direct. So how's this playing out in the public realm? We're seeing a ton of changes. So with Title 24, 2022, which is churning towards being fully adopted and enacted, of course, we're seeing once again upping the ante. And a number of years ago, in a meeting with PG&E, we had a code expert draw a graph for us of how the code changes were amplifying. And it was a curve that started out low, changed a little bit, and hit an inflection point, I'm going to say about 7 or 8, 9 years ago, where the curve of change really started to increase steeply. So we are going to continue to see more dramatic increases in the Title 24 requirements. We're seeing, and actually since we first drafted this slide deck, I realized the second purple box on the left now has been changed from 2045 to 2035 by recent acts of Governor Newsom. The CEC, our California Energy Commission, has created two very important funding programs called Tech and Build, which are going to have a huge impact on us. And I believe we're now up to either 51 or 52 REACH codes or natural gas bans enacted by local jurisdictions, some of them within the Tri-County area. So all of these programs, policies, mandates, incentives represent a very rapidly evolving culture that we work in the building industry. And over to Jay for a few comments.
Yes, well, our home is definitely on fire, and the International Panel on for Climate Change calls for something called unprecedented action. And just by comparative, it is possible. If you look back at the chart that is here, in 1939, the entire U.S. military produced just under 3,000 aircrafts. Click, if you would, please. By mid-1944, they were producing 3,000 aircraft every 11 days. The equivalent for us is in 2020, we added 40,000 megawatts of new renewable energy. If we change this pace by 2025, we can be adding nearly 1.5 million megawatts. That is the scale that is there. Advance, please. So it is possible. And the keys to making it possible are the vision of where we're going, the engagement of virtually everyone, and the commitment to get there. Well, some of you will, Ann and I do, remember when Kennedy said, let's get to the moon in this decade. He said it, and it was his vision, and everybody got behind it and moved forward. And on July 20th, 1969, astronaut Aldrin walked on the moon and returned safely. So this unprecedented action is not out of reach, and we know how to do it, and that's part of what today is about. And in fact, your being here today is a step. Back to Ann.
Okay, so moving on to our what this means for the building sector, another vehicle metaphor. We need to make some shifts. So we'll talk about what those are. I wanted to start with this animated graphic, and I think it'll allow me to repeat it a few times. This was developed by a colleague, Stacy Smedley, and it's really fantastic because it shows at all the stages of a building's lifetime when emissions occur. And so we have an opportunity to work at the emissions equation at all of these stages when we make decisions about buildings. So without spending a lot of time here, you all will have the PDF, you'll have the animation, and I think it's a really nice tool. But so we talk about manufacturing. So again, building products, moving the products to where they're going to be installed, then the operational stage of emissions when the buildings are actually burning fuel to heat, cool, and run various other equipment, pumps, and so forth. And then, of course, end of life stages. So these are all important. So we're going to talk about the shifts that we need to get to high performance with regard to each of these, the fuel sources, the embodied carbon, high efficiency, technology footprint, which is a term I've coined here. And I hope when we get to that topic, it will make sense. The timing of energy use, and also resiliency. We need to make all these shifts in an incredibly short window. So we'll need to be animated like that graphic, the GIF on the preceding slide. Okay, so fuel sources. So we need to eliminate fossil fuels from buildings. And probably most of you have heard quite a lot about this already, but just to reiterate for those of you who may be a little bit new to the conversation, this means no more gas common items, right? Things that appear in most homes, furnaces, water heaters, clothes dryers, stoves, cooktops, things that are maybe less common, but still far from uncommon and are part of the equation as well. The fireplaces, pools, spas, barbecues, and then we get into equipment, leaf blowers, lawn mowers. So there's a ton of this work happening at state level at municipal level, and also through individual action by players in the building industry to move even ahead of the incentives and mandates. So we have, there's a lot going on here. And by the way, I should mention, we're touching on each of these topics very rapidly because we felt it was worthwhile to cover a lot of content for you all. So this is not a deep dive on anything. It's more kind of the 30,000 foot view of all of these sort of changes and what they mean for us. So in terms of embodied carbon, once again, we have only about 8 years, and I'm reiterating that point here simply because I want to point out how this graph of showing the relationship between embodied carbon and operational carbon really demonstrates that this embodied carbon, when we look at it through the first 10 years of a building's life, so from the left side of the graph to this vertical dotted line at 2030, we can see that the emissions profile of a building in that first 10 years is dramatically dominated by the embodied carbon. So this means within this 8 to 10 years that we have to turn this very big, slow, cumbersome moving ship around. This needs a lot of our attention. And so this, I think, is helpful in illustrating, well, what does that mean? So the graph here on the left shows the relative carbon profile of big, heavy buildings at the left, smaller, light buildings in the middle, and then building renovations in the bar graph on the right. And you'll see that existing building renovations entail dramatically fewer carbon emissions than building new buildings, even small and lightweight ones. So the takeaways of this for me are we should really only be building what we absolutely need right now. And what we do need should be focused on rehabbing and repurposing existing buildings, and that a lot of that rehab and repurposing work should focus on reductions in operating carbon when we make those building renovations. And of course, whatever design we do for new buildings needs to be very embodied carbon savvy. So that means choosing low carbon materials. And of course, one of the most important, or arguably the most important, is the concrete. And a lot can be done to reduce the carbon footprint of concrete. So we won't go there now, but again, to raise the flag, there's some great resources on how to do that. Now, moving on to technology footprint, and I want to start by pointing out the definition that I've shown up here at the top. Technology comes from the Greek word meaning systematic treatment of an art, craft, or technique. So we tend to use technology in a much more limited way in our everyday conversation, where we often mean high tech and electronics, computer stuff, right? But technology is a much bigger thing. And what I'm showing here as the technologies that we have range from low tech and low impact on the left to high tech and high impact on the right. And what I mean by impact is having higher carbon emissions associated with them, higher energy demands, higher material demands, and so forth. So we like to work from left to right because the more effective we are at employing the strategies starting at the left side of the spectrum, the fewer of the higher impact, higher technology strategies we need at the right-hand side of this spectrum in order to achieve high performance buildings. So it may seem kind of counterintuitive that we want a high performing building, and yet we're going to be starting with the most low tech and low impact technologies in order to get there with least impact. Okay, and we'll talk a little bit about what some of those are later on in the how to implement section. Meanwhile, moving on to the next topic, energy time of use. So we've thought, and I think those of us who are Californians have long been aware, working this industry, that the state cares, and therefore we need to care about how much energy our buildings use. And yet in the last few years, what started to happen is the light has dawned that we need to be concerned not only with how much energy we're using, but when it gets used. And this diagram referred to as the duck curve really, I think, describes why this matters. So what this shows is the belly of the duck is what's referred to as solar overproduction. So what happens in the middle of the day, so starting at about, when the sun comes up, 8, 9 a.m., we start dipping down, and around 3 in the afternoon, the belly of the duck reaches its fattest point. And what that means is we have more energy being produced than we can necessarily use at that time. Meanwhile, the sun goes down and the solar production drops pretty rapidly. And then we have a need for other types of energy generation, which are dirtier than solar, to be brought on board quite rapidly. So we're relying on older power plants, and particularly when we hit peak loads at peak days. So for example, for summer cooling, then we need to bring on some of the oldest and dirtiest power plants in the state in order to meet our peak demands. So what that means is we're going to be focusing in the future way more on what's called demand response. How do we make our buildings and systems responsive to those changes in demand over time and help to even out the energy use curve, reduce the belly of the duck, and reduce the ramp in the afternoon. So demand response programs are still pretty much in their infancy. And so you probably haven't heard very much about them, but we're going to see more and more. And the way that I think we're starting to see them without necessarily even being aware is that we're starting to buy smart appliances. And one of the reasons those appliances are referred to as smart is that they are enabled with demand response capability. That said, in most places, the demand response programs are not yet in place, but they will be coming on, and there will start to be more of a dialogue with utilities about how the objects in our homes are being controlled in response to the grid. And it's never command and control from the top. It's usually enacted through an agreement between the customer and the utility, so that you have options about how you participate in demand response. However, in the shorter term, those who have solar on their rooftops or on their properties have an opportunity to start to play in this grid responsive way through what's called solar self-consumption. So when we have solar, if we add batteries, then we're able to use some of that, call it belly of the duck energy, to supply our batteries during the peak day when we don't need them for whatever is happening on premises. And then to avoid that utility ramp in the late afternoon, early evening, we can begin to use our batteries and thereby help out the grid and also avoid some peak utility charges at the same time. And of course, solar with batteries also has the additional benefit of emergency backup. And this has become quite important to many Californians who've been affected by the public safety power shutoffs, the PSPSs, that have been a regular feature of life for many California residents over the last few years. So we're seeing a lot more demand for batteries. We also have what's potential to utilize what's called thermal storage. And there are 3 types of thermal storage that can potentially be deployed in our buildings. Heat pump water heaters with smart controls to say, let's store some extra hot water during, again, the peak period that can be utilized later on as a form of thermal energy storage, as is thermal mass, demonstrated by this cute little graphic at the bottom left. The most common form of thermal mass in our buildings might be a concrete slab or even the drywall in the walls, various types of masonry, carefully deployed so that the solar energy can come through glass, hit the thermal mass, and then dampen the heat by absorbing the heat energy into that thermal mass, which will then slowly give the heat back as the day cools. So that's can be challenging to design effectively. So I wouldn't encourage you to venture into the use of thermal mass without careful study of how to utilize it correctly. But it can be a very useful tool. And then phase change materials, which at the moment are relatively uncommon and inexpensive, but have a real potential to operate in much the same way that thermal mass does, but using a slightly different mechanism, what's called the phase change. So changing something from a solid to a liquid, and then having it go back to a solid has the same sort of functionality as thermal mass, where we're absorbing heat and then re-releasing it when it's strategic. Okay, and the last topic, I think, in this sequence of big strategies, big place strategies in our buildings is to look at resiliency. And primarily what we are interested in the current times. There are certainly other vulnerabilities that are of concern in the longer time horizon, but we're dealing with extreme heat, again, wildfire, smoke and air pollutants, power outages. So what's, I think, interesting and I guess illuminating about all of these vulnerabilities is that they all involve thermal enclosure as part of the solution. So extreme heat means we're doing a really good job with air sealing and insulating. Dealing with wildfire means we're going to do some other things to harden the enclosure. And smoke and air pollutants, of course, again, it's about air tightness as well as filtered ventilation air. And then power outage, once again, we're interested in a robust thermal enclosure because a power outage can mean loss of heating and cooling. And so we want to stay healthy and comfortable, and as well as energy storage. So this all leads to the conclusion that the high performance enclosure is really our absolute highest priority and first line of defense in terms of achieving resiliency. And Jay later on will say a little bit more about the importance of air sealing, as well as some other related topics. Over to you, Jay.
Thank you, Anne. Anne mentioned earlier on a slide, just a few slides ago, there was to begin with passive measures and then go to active measures, or as it was there, and the loading order of high performance. Click, please. The loading order of high performance is exactly that. Anything that you can do that is passive, you do first, because it doesn't require ongoing energy to keep it operating. Then you do the active thing second in the order that Anne described. And then you put renewables on after you have reduced the energy usage as much as you possibly can. Click, please. Many of you, depending on how old you are as an architect, architects have known for years about passive solar, which is siting and orienting a building and providing shading so that it can take advantage of the winter sun to heat that thermal mass that Anne spoke of. But it blocks the summer sun from entering through the windows in such a way that it prevents the summer sun from overheating. Interestingly, if you look at cave dwellers from back a few centuries ago, you find that when possible, there are more caves oriented facing south than there are any other direction, for this very reason, that it kept it a little warmer in the winter and a little cooler in the summer. Click, please, again. The name is really in passive. As you know, I work with Passive House, and a passive, something like this thermos here is passive in that it keeps the heat in the coffee or the cold in the iced tea without doing anything. The alternative, of course, is an active system like this little coffee pot that you see here, where it does keep the coffee hot, but it's using the electricity until finally it burns the last coffee, the last coffee in the jar. So thinking in terms of a passive solution is something that delivers a desired performance naturally. And here's a couple of examples would be the wing on a race car. Once the race car has a wing on it, it is pushed down with speed so that it can go faster through corners. It has better traction, as though the car were heavier, but it's not really heavier, it's just being pushed down. And as long as that car is driving, as long as it's going through corners at speed, it will have increased traction. It's a passive solution. The one above on the right is reverse diagonal parking. I'm not sure that many of you have seen that. It's not a hockey stick growing trend, but it is coming. Because when you see this is at a park area you see here, and by backing in, you don't eliminate or even reduce the number of fender benders, but you dramatically reduce the number of personal injuries, of people being hit by cars accidentally. Because when you go in on the other angle, you wind up with the doors open toward the back of the car, and the back of the car is where the picnic basket is, and the bicycles and things like that. Go back if you would, Ann, please.
I was trying to figure out how to do that, but I'm not succeeding. So, oh, there we go.
Oh, there we go. Well, I wanted you to go back because the point I want to make with this reverse diagonal parking, by the way, it works for as long as you're parking cars there. There will be fewer personal injuries because the kids are directed by the doors to the back of the car, and you're standing back there loading the bike, et cetera, et cetera. But the other point I make is that imagine how much more expensive it was to paint the lines in the reverse direction. A huge percentage of passive things that you can do don't cost any more at all. They're just changing priorities. And I wanted to bring that up. So thank you, Ann, for going back. Now we can go forward. Another example, this is actually a build back from the fire, a home that was destroyed in the fire a year and 2 months ago up here in Santa Cruz. And the elements that you see going in there are modular components that come already with the insulation, the air sealing, the permeable membranes to allow moisture to escape where it needs to. It essentially in about 4 or 5 days, they can assemble that entire envelope that is so important, as was mentioned in the previous or earlier just a few moments ago. Click please, Ann. We can get away from that one and come to resilience we talked about. I like to think of, I was a pilot at one time, so I like to think of that resilience is a resilience of a passive house is like the glide slope of a glider. An airplane will glide when it loses power. All airplanes do. But if you're, say, 3 miles in the air, like a Cessna 172 or a fighter plane from the Air Force can glide about 7 miles forward for every mile of altitude it loses. So a small plane can glide about 20 miles. So you have about a 20-mile radius where you can find a safe place to land. A commercial airliner is a little over double that. It's more like 40 or 45 miles that it can go. But a glider will glide for over 200 miles in any direction. And in the same way, a passive house, if you lose your power to heat the house at 70 degrees outside and really cold outside, a normal home without heat stays livable. If they think of 40 degrees as livable. And if the home was built in 50s, it'll last about 8 hours before it gets below 40 degrees. A 1980s home, we were better. We began putting insulation and things in 24 hours. A 2009 home, almost 2 days. And click please, if you would, it should add the other that's there. A passive house will go for 154 hours, more than 6 days. So you have a lot longer to take care of things and to recover if you have the opportunity of a fire in the fireplace or just things that you can do to keep warm. So it's that resiliency, that additional time to deal with the loss of heat or power is a very important factor, and it's all about the envelope. Back to Ann then.
Yeah, I love that. All about the envelope. We'll probably hammer that nail a few times today. So how to implement high performance. So we've sort of broken this down into 3 concepts, the 3-legged stool of high performance, if you will. The first being the new loading order. Loading order is something you may have heard in the past. Secondly, building science. And then thirdly, integrated design and delivery. So, but before we move over to those, I wanted to share an epiphany I had a few years ago. I was working on my book about zero energy homes and reading a lot of studies. And I realized that the premise underlying many of these studies was well, how much would it cost to get to zero net energy? And I thought, well, that's the wrong question. The question is really, what do we need to do differently to achieve that goal within budget? And so, fill in whatever your high performance goal is, whether it's passive house, zero net energy, living building challenge, LEED platinum, whatever the goal is, it's all about making choices to enable you to achieve a goal within a given budget. So I think it's really important to reframe the way we approach a problem. So if you're thinking, oh, high performance, it's hard enough to just meet code, it's really all about asking the right questions. And there's a wonderful article, there's a link here at the bottom left where you can go read this article, just very eloquently makes this case by the architect Bruce Coldham, who's retired a couple of years ago, but really a pioneering practitioner in the Northeast. So, and Jay's got a few more illuminations about this.
When looking from the outside of a home, you really can't tell what the performance is. So we've got essentially pictures of the same home that's here. But this will be helpful, hopefully, to architects who would like to build high-performing homes or better high-performing homes or buildings. It's difficult to convince someone to spend a little more to do things like that. So we've gotten into that. We sort of worked into selling high performance as an upgrade. Here's a normal home, and you can have a high performance home if you'll just spend a little more. And it runs around 5% to get to that. But what we really want to do, go ahead and click. Thank you. What we really want to do is treat the high performance as the baseline, where you're saying you've got a high performance home that's here. You'd like to downgrade, what would you like to downgrade? No, you've got a high performance home, and click please if you would. You can say that, yes, you can reduce the cost a little, but you're giving up some value. Click again. And I love the idea that you're saying, so what is it you'd like to give up? Energy efficiency, the quality of the air that you're breathing, comfort, resilience, peace of mind, resale value. People don't turn down, people love to get things. They don't like to pay for them, but they hate to lose things, even if it does give them some money. We were much more inclined to stop loss than we are to go forward. Click if you would, please. Imagine if the baseline Toyota, and this is what it was in 1959, the baseline Toyota came, and would you invest 5% more to get the airbags and anti-lock brakes and safety belts and things like that? It's now, of course, required instead. That is the way cars are built and sold, and that's what we need to do with the houses that we're talking about. Is start with the baseline of building to what is possible, and then back down if you have to. But most people will not choose to do that back down. There are upgrades. Equivalents of a house thing are your countertops and your cabinets and the carpet and things like that. We need to get it to where that's what they're choosing to invest more in, but they are not going to lose or not going to step back from the passive house or the high performing elements.
What I love about that is how Jay's used other questions, again, to sort of show how you frame the question really changes how people are going to respond to that question. So to move on to the idea of the new loading order. So we need to prioritize in a given order in order to minimize utility costs, which is hugely important. I think no one in recent times can possibly have escaped the global message that we need to start to redress the inequities in our culture. And so again, those who can least afford utility costs are those most often burdened by high utility costs. And secondly, we also need to prioritize this order in order to, again, maximize the passive survivability, or again, the resiliency features that we've been discussing. So the order, in my view, and Jay and I differ slightly on this, I think he would reverse the first two, but for me, it's minimizing embodied carbon first. And I already mentioned that to build only what's needed, to be looking at structure in the leanest possible way, because structure is where the most embodied carbon exists in a building. and choosing the lowest carbon materials. And I want to distinguish between leanest structure and lowest carbon materials, because how you design the structure can have a tremendous impact. A colleague of mine who's a structural engineer and I were working on a project together quite a few years ago, and he had designed the foundation for this new building in the way that he felt was most efficient, the most efficient use of materials. And then our client, who was very astute, said, yeah, but have you factored in transportation and off-haul of excavation materials? And he said, I actually haven't. Went back to the drawing board, did those calcs and said, you're right, and redesigned the foundation differently to minimize the excavation and off-haul, because it turns out that that transportation impact, which entailed a lot of vehicle emissions and miles traveled, really had a huge impact on the overall embodied carbon of that foundation design. So that's not just about the materials, it's about the thought process that goes into the design. So secondly, optimizing efficiency. So once we've figured out how to minimize the embodied carbon, we want to make what it is that we build as efficient as possible, starting with the building geometry itself. And I'll say a little bit more about that in a minute. Also, again, the enclosure or the envelope, we use both of those terms interchangeably. Heating, ventilating, and air conditioning, water heating, and of course, again, filtered ventilation air. So all those things have efficiency components. Then looking at all electric operation in order to decarbonize those buildings, and mentioned these factors earlier as well. Moving to renewable energy, Jay pointed out earlier that the order for sustainability is to go from passive to active to renewables. And renewable energy can either be produced on site or purchased as clean energy option from your local utility or community choice aggregator. And fortunately, those clean energy options are becoming increasingly available across the state. And then finally, moving to energy storage when we can. And again, that could represent any of these things we've mentioned already, batteries, including eventually we'll be able to use the batteries in electric vehicles to supply power to our homes as both as emergency backup and to provide the grid services that I mentioned earlier. And also, again, water heater, phase change materials. So more about the efficiency inherent in building geometry. So this was a fun project I worked on for Stanford University a few years ago. They were building a bunch of faculty housing, and on the north side of the street, which in this image is down, that's not the usual way, but well, it's flipped around. There were existing homes that were felt to be important to echo in the character of the new homes at the south side of the street, or the upper part of this diagram. So I was brought in after the designs had gotten to this stage and was asked to review the designs and provide input along with another colleague of mine on how they could improve the energy performance. And I said, well, so take a look at the roof plans here. What do you see? And they kind of said, well, I don't know. And the rest of the story was if you looked at the elevations for these, it looked as though they had done a really excellent job of echoing the visual character of the existing homes on the north side of the street. But when you looked at them from this angle, you can see that there's a great deal more complexity in these new home designs. And they hadn't factored that in at all. So there are a lot of costs associated with this complexity, all of which I've enumerated on the right. And so they were really pretty shocked. This was a very senior development team at Stanford. Never for a moment crossed their mind what this represented in terms of all of these costs, risks, and liabilities. So to carry this a little bit further, just kind of for amusement value, I looked at this in a much more simplified way. And I said, okay, well, let's try and quantify this a little bit. And for the sake of argument, these costs are probably low now, considering what's been happening with costs lately. But at the time I originally developed this, these were, seemed reasonably plausible to folks that I talked to about them. So I said, okay, let's say that for every additional foot of perimeter, we're going to have to spend another $300, and for every additional corner, an additional $500. And completely disregarding other cost impacts, say, that are happening on the interior, the roofing, the design, let alone utility cost or maintenance costs to the homeowners. I did this comparison of 3 different plans, each of which represented a 2,500 square foot, single story home. And you can see the comparisons below. So the plan A, the simple rectangle, had 200 feet of perimeter, 4 corners. Then we get to plan B, 220 feet of perimeter, 8 corners. Plan C, 250 feet of perimeter and 18 corners. And using these figures, hypothetical figures on the left, you see these represent respectively an increase of $9,000 or $15,000. And what we saw up here is a lot more complex than that. So there's a lot of cost that's going in without any thought for what that represents in terms of money that could be spent on other issues like resiliency and high performance and thermal comfort. So over to you, Jay.
Okay, the envelope, and we continue to talk about how important the envelope is. And here's another reason that it's so important, is the envelope is generally a 100-year decision. A building lasts not always 100 years, sometimes over, but if you think of it as a 100-year decision, you realize that every year, if things that you do right contribute year after year, things that you do wrong cost year after year. And because policies are changing, if you're building something today that's going to be illegal in 10 years, why would you choose to build a retrofit? Why not reach out forward and build to what we know to be the state-of-the-art building science today? Click, please. So we're talking about the envelope. I think a lot of times homes or buildings get designed from the outside in. And it's great to decorate the envelope, but not to decorate with the envelope. You can wrap an envelope. What you've got the box here that is sealed, it's taped, it's protecting what is inside in the way it is supposed to, and you can make it beautiful with just silver and silver, or you can make it wonderfully. You can be as elaborate as you want to, as long as the box inside is providing the things that are there. It's possible, click please, it's possible that you can overdo the things that you do on the outside that cost additional money or do things, or click one more time, or just build a building to contain what it is that you've got there, one more click, but those are unacceptable. You want to, decorating the envelope is terrific, but not decorating with the envelope. One of the things that happens is a lot of homes that are being designed from outside in, click please, we use windows as a part of the design element. And windows are not only more expensive to purchase, they're more expensive to install. You see the corners associated with that bay window there. But you've got this extra effort to make sure that it's air sealed and that it's working. Windows have a purpose. It's to bring in the daylight, to have fresh air, the views, or to escape the egress. When you're designing something, make sure that the windows that you're putting in it meet one or more of these needs. And if they don't, they're adding expense and difficulty that's going to last for years and years and years. Click, please. The envelope is like your protective equipment. Click again so that we get we're all familiar with what PPE is now, and over the last 2 years, it's a personal protective equipment. Well, click one more time. The envelope itself is a personal protective envelope. As you see here, the red box, if you will, that's broken by windows is the envelope itself, and they're doing things in it with air tightness, with the high performance doors and windows, the thermal bridge free, climate specific insulation, and heat recovery. It's an important way to go. Click again. The envelope's job really is to provide resiliency. A fireman running into the fire with the heat and the danger that's there for him or her is wearing an envelope. The same is true of an astronaut. If you click for the astronaut, that's a very hostile environment in outer space, not much air to breathe, and it's pretty cold. And what you have there is, in the third click, is you have an airtight shell that's there, but you could make an airtight shell with saran wrap. So you don't want to do that. You need insulation in that shell so that it protects the escape of heat from in the case of the astronaut, or the intrusion of heat from the case of the fire person. And then you also want continuous fresh air. The continuous fresh air is active, but the airtight shell and the insulation are passive. Click, please. So the envelope, it's really about air sealing, and describe some of the things and the cost associated with it. All of the things in this diagram on the right, and see in the green there that it's a free download, you can get this. They provide the details of how to build it, and everything that's built there is passive. You made it right to begin with, you did the details right, and so that's going to perform the way that you want it to for as long as it's there. Thermal bridging is another issue. Click if you would. If you've ever tried to pick up an iron frying pan that you just fried something in, you know that even though the handle of the frying pan wasn't over the heat, it's hot. And that's the thermal bridge. And of course, iron or in any kind of metal is a good bridge. The pictures, both pictures are thermal images. And on the left, it's a house, and you can literally see where the studs are in the wall, because they're passing, the more heat from inside is escaping to the outside. You can see around the windows, there's some issues with the windows, and at the top there's a cap, and then at the bottom, I'm going to guess that they have a pretty leaky HVAC system with the heater ducting leaking in the underneath the home, which keeps the gophers happy, but it's not good for saving energy. On the right is a building that is really, they took a lot of attention. You can see how dark the building is. Again, it's another thermal photograph. They did a great job of insulating the walls and things, but they didn't pay attention to the thermal bridges to the decks that are there. And so, 24 hours a day, 7 days a week, 365 days a year, that building is leaking the heat out when it's cold and leaking the heat in when it's hot. It's like, a leak in a faucet leak is not a big deal until you realize that it goes on day after day and year after year. And that's what we have and what we experience if we don't do our thermal bridges correct. Click, please. One of the things that we also do that I'd like to talk about is heat recovery ventilation, where you take air on the outside. There are different temperatures. So click to put the temperature up. Let's say this one is a 90% efficient. So there's air on the inside is 70 degrees as it starts out through the exchange. Click, and it's coming in at 30 degrees. The air doesn't mix, it doesn't mingle. So you don't get the stale or the moisture or things that are in the air that's going out, doesn't cross into the air coming in. 2 more clicks. But the air that comes in, that 30-degree air, warms to 66 degrees as it comes in. And of course, the air cools going out. It's exchanging it through a heat exchange system. And I say again, the air doesn't mix. And note that it's 90% efficient. The point I want to make here, particularly for those of you who are for those of you who are specifying systems like a heat recovery ventilation system, that if you get this, the value engineering that somebody finds we can save several $1,000s by getting an 80% efficient for an HRV instead of a 90%. And it sounds like it's small because we're thinking in terms of from the bottom up, 80 to 90%. But click. But if you look from the other end, from the top end, it's a much larger difference. Click. Because you wind up literally doubling the energy that's required to heat to heat the air that's coming in and get it to where it needs to go in the building. While we're kind of on the topic of graphs, if you will, if you'd click again, efficiency, 90% efficiency is important. And Passive House last year, the International Passive House, came up with the concept that efficiency is really the first renewable energy. So imagine that you have a home that's a 2,000 square foot home, and it uses 500 kilowatts of electricity a month, about 6,000 kilowatts a year, and you choose to add renewables, and you've got roof space so that you could reduce your annual usage, where you could cover half of your annual usage 50% of it with those renewables. Click, please. That's just so that 50% of energy you're no longer using goes on year after year after year, and it's free. That the least expensive energy always is the energy you don't use. Click to the next chart. Take that same house, and instead of simply just adding solar, you employ efficiency measures like sealing the envelope, adding insulation if it's necessary, doing things, going to all LEDs and changing behaviors and putting things on timers, and this, all of the things that you can do to lower your energy use, and you get rid of 50% of that annual usage again if you click there. It is the same as if you'd put solar on your home, except it has the same outcome, and both approaches go on year after year after year and are carbon neutral. So I think efficiency really is the first renewable and a smart thing to do. So if you're thinking of solar out there, make sure you make your home or building as energy efficient as you can first, then add the solar. That's passive, active, then renewables. And back to Anne, I believe, at this point, don't we?
Okay. Yes, thank you, Jay. That was really great. I will comment though that I think sometimes there's an exception to doing efficiency first. Sometimes with existing buildings, the efficiency, it would be ideally done first, but it becomes really challenging and invasive. And if people do solar first, I've joked and said, sometimes solar is the gateway drug. They get excited about having solar and then we'll go on to make efficiency changes as well. Again, less than ideal, because if you do efficiency first, you can have a smaller mechanical system. And if you do it later, you're sort of stuck with whatever larger system you had. But definitely efficiency first is an excellent premise, and recognizing that everything has the exception. Okay, so moving on to building science. I thought this was a really fun image. I can't remember what keywords I used to get it from Wikipedia, but I loved it. So clearly the dog is more than the sum of the parts, how it's assembled matters. And particularly if we want it to work right, to be fully engaged with the world around it and interacting with its environment as it should, we want the assemblies to go together properly. So in buildings, this is the probably fastest ever discussion of building science, but I wanted to point out that 3C Ren offers many classes on various aspects of building science, and I cannot heartily enough recommend that you take as many of those classes as you can, because it's a pretty complicated subject and there are lots of opportunities to get things wrong, and it's really important that we get them right, particularly with all of the increases in code requirements. Those generally represent more opportunities to get things wrong. So physics rules. This is the bottom line here, that we need to put our assemblies together properly in order to make sure that we're not creating problems while we're trying to solve other problems. So the primary job of all our building assemblies, roofs, walls, foundations, window assemblies, any openings, is to control the movement of water, both bulk water and water vapor, to control the movement of heat, and to control the movement of air, so that we can maintain both comfort and health and the integrity of the enclosure within. So these diagrams at right aren't necessarily intended to be recommendations. They're examples pulled from finehomebuilding.com, simply showing that there are a lot of different ways to do assemblies, but in all cases, getting the building science right mattered. And Jay mentioned earlier that this has to do with the air, vapor, and water permeability of each of the layers and how they stack to be appropriate to the specific climate and building needs. So how we achieve, in my mind, an effectively designed enclosure and assemblies is via an integrated design and delivery process. And so for those of you not familiar with the term integrated design and delivery, what I mean by delivery is getting the building built, commissioned, and turned over to the owners and occupants. So it's not all about design, much as those of us who were trained in the design professions might like to think so. Our collaborators in the construction side of things are also tremendously important in getting the results we want. And I like to describe this as a genetic problem, that if you have both parents, so to speak, the design parent, if you will, and the construction parent share the high performance gene, you'll come out with high performance buildings. If either parent is missing that gene, you're not going to have the high performance result. So I'll say a little bit about why that is. Well, first of all, what do we mean by integrated? So buildings that perform well. So all of the parts of the building work together and are mutually reinforcing. Well, we get there only if we have a team that's also well integrated. And so what this means is, rather than working in sort of the traditional handoff process that we have, most of us, been sort of taught through our professional careers in the building industry, we're trying to be more collaborative. We want people involved from the beginning, so we really benefit from the collective knowledge, experience, and insights of all the team members. Because when we're striving for high performance, inherently what we're saying is just meeting code, being barely legal, isn't good enough. High performance means striving for a higher bar so that we can have better performing buildings, happier and healthier occupants, and a livable planet well into the future. So the reason I think this is important is because there's a myth that we deal with in this industry, and that is that design happens and then construction happens. There are separate processes, and they join one another, but one happens first and the other follows. The reality is, in my experience, that design happens all the way through construction, and we need construction knowledge from the very beginning of design in order to achieve a buildable design. So when I'm in a live classroom full of people, the fun thing to do is I'll say, okay, so has anybody ever encountered a set of drawings that embodied every design decision that was made during the course of having the building be built? Never, not once, has anyone ever raised their hand. So this means that, yes, design is happening all the way through the construction process. And again, without that reality check, I've certainly worked on projects or been exposed to projects where the construction knowledge was not fully present in the design process and emerged as problems later on. So we really need all that intelligence from the beginning to optimize projects. So that means we need everybody, all the key players need to be involved very, very early. So architect, the designer, the builder, the contractor, and all the players who have significant roles otherwise, the consultants and subs. They all also should have experience that's comparable to the project in hand. So this is fun. So this is George Kurtzen. George is the superintendent for Habitat for Humanity of Greater San Joaquin County. And on George's projects, he wears all the hats, literally and figuratively. So he designs, he plumbs, he installs, he manages construction, he does the air sealing. So this is ideal, but George is highly unusual. You will not find very many individuals who actually have all the capabilities necessary to achieve a high performance, highly efficient, comfortable, building that's got full enclosure integrity and so forth. So George, as I said, is pretty exceptional. That said, you're not going to find most building teams have one person on them. So in reality, what we need is a team that works well together. And through, 30 plus years, no, I'm going to make that 40 plus years in this industry. What I found is the teams that work best have these 4 characteristics. They are committed, they're creative, they have a good body of experience, and they're very engaged. I use engagement as a shorthand for this plays well with others, because I can remember 4 things, 2 C's and 2 E's, commitment, creativity, experience, and engagement. It's a little bit harder to remember more than that. But this one is my checklist when I work on teams, is to sort of say, okay, do we have what we need? And if we're lacking in any of these areas, the only area where I think we can make a sacrifice to some degree is an experience. So as long as you have a good body of experience on your team as a whole, there can be team members who aren't necessarily super experienced, so long as they are fully there in terms of commitment, creativity, and engagement. But otherwise, it's really, really hard to achieve a high bar of performance without these traits. All right, so you got the right people together. What does an integrated process look like? First of all, and this should probably be in bigger type and bolder colors, the owner, whoever's controlling the finances, has to commit to an integrated process. Otherwise, it won't happen. It will be disintegrated instead. Put together the team, mentioned already. All these diamonds represent charrettes or workshops where we come together as a team to work through design decisions. And then these kind of spiral diagrams with littler diamonds represent smaller gatherings of parts of the team where we work through iteratively design until we actually believe we've achieved resolution. And I like the image of the spiral stair, because what I've found in integrated projects I've worked on is that there's a tendency to revisit certain issues. And so people may think, well, haven't we been here before? This is very familiar. Well, you may be there before. It may seem a familiar issue, but you have made progress. You're climbing to the next level, and you'll revisit until you achieve resolution. What this means is that we may spend more time in the front end. So in the pre-design phase, the top left green box, where you see the integration, the different colors representing different building systems and the people who work on those systems. So we iterate through those till we really get it right. And then what that means in the long run is, compared to the conventional process shown in the bottom half of the diagram, we can spend less time in the CD phase doing the construction documents because we've really worked through this. So there are a number of benefits that come along with that. So you might not save time overall, but what you're doing is you're achieving a higher level of shared understanding. So the diagram on the left, well, both of them show time on the x-axis and then common understanding on the y-axis. The typical process shown on the left, we show that common understanding increases fairly slowly throughout most of the project and then reaches a peak about the time the project is over. So suboptimal, to say the least. The diagram on the right shows that when we get everyone involved early, we achieve common understanding very, very early on and maintain it at a peak level throughout the rest of the project. So I think it's pretty intuitive to show that this really results in a much smoother process, much easier way of achieving high performance outcomes, and carries with it so many other benefits, some of which I've highlighted in the purple box at the bottom there. I can't emphasize enough how different the process is in eliminating risks and conflict and confusion and change orders and all the negatives that go along with that. So it saves money as well as time. I already mentioned that, well, the time in the construction document phase. So why does it save money? The McLamey curve here, I think, describes that. So this was created by Patrick McLamey with HOK Architects many years ago, and is very, very timely to this day, timely and relevant. So he shows how on the left axis, vertical axis, we go from low to high in terms of the effort, the ability to affect or impact the project. On the right side, it's the cost of design changes, and time, again, along the x-axis. So as the time progresses, we find that our ability to make changes diminishes pretty rapidly. Meanwhile, costs increase pretty rapidly. So we want to concentrate all our design decisions within this early part of the project, where we can make changes that have an important impact on the project and still at relatively low cost. So that is a key piece of this. I'm going to point to, there's another linked resource on this page, an integrated design and delivery guide developed by the Commission for Environmental Cooperation, which is a trinational cooperation between the US, Canada, and Mexico. And it breaks down the integrated design and delivery process by various roles in that process. So I'll point you to that as a further resource. Another description of why it saves money comes from Amory Levins, who describes this as tunneling through the cost barrier, and shown here once again from Bruce Coldham of Coldham and Hartman Architects in the Northeast, how when they, in their early innovations, initially they tightened up the envelope, added some cost, added insulation, that added more cost. They went to triple glazing, that added more cost, except then they realized that enabled them to eliminate or greatly downsize the central heating system, dropping the costs back down. So there, that is an important takeaway. Here's an example from Bill Reed and the 7 Group, who published a seminal text on integrated design and delivery. This example was, this project is the Pennsylvania Department of Environmental Protection schematic design of the building. And there was a discussion with the group about the mechanical system, because it was an integrated process and they had the mechanical engineer in the room from the beginning. They said, well, we were thinking we'd put the mechanical, enclosure on the roof. And he said, well, you could do that, but if I can get it inside the building enclosure, it will, the system will perform much, much better. And they said, well, it's a very tight site. Well, the architects, well, we could add this, a very skinny band, 18 inches on each end of the building, these pink bars, to enable us to put these mechanical closures inside. That decision, which was a collaborative one involving multiple disciplines, saved them not only $40,000 in first cost, but reduced operating energy for the life of the building. So there are several morals of this story. Pursuing an integrated process, you kind of can't help but have good outcomes, does require the involvement of the right people, the committed, creative, experienced, engaged. And by the way, don't try to leave anybody out, because that will backfire on you. And my last one, if it ain't in black and white, you better get it in your drawings and specs, or it won't happen. Over to you, Jay.
All right, thank you very much. Well, click if you would, please. The old model, as this is kind of a repeat of the concept that Ann just went through, that we used to start with the owner or the homeowner, they know what their needs and priorities and things are. Then they try to transfer that vision to the architect. The architect then does the design process and transfers the vision to the builder. But click again. But if you get them started in the beginning, as they work together, as Ann said so eloquently, click, you wind up with the vision being much more achievable, and everybody comes together, and it does save money, time, and energy in the overall. Click, please. Evidence-based performance is kind of, it's another way of looking at the integrated design that Ann was talking, that Ann spoke of. Is you set your goals beforehand, then you model as often and as early as you can, reiterative modeling, so that you know what it's going to cost and do in the beginning, and you can deal with the potential of expense going up or down as you go through with the value engineering of which I spoke. Then you test everything to verify that it's going and then doing what it wants to, and then for afterwards you monitor the performance and experience to make sure it's doing what it should be doing. So change is happening all the time. If we go back and think about the evolution of sustainability, if you will, back in the 60s, we were thinking about what we ought to do. There was activism, the Environmental Defense Fund and Greenpeace. Then we learned from Energy Star, LEED, Build It Green, we could choose it, prescriptive standards, do this, get an Energy Star of that, do these kind of things, and that helped us get better. Then we moved on to certification programs like Passive House or Living Building or WELL or Reset, where you actually measure things and you prove that the performance was there. And now, in fact, we're being expected to prove it for sure. In New York, starting in 2025, you will have a building budget for your new or existing building, and by legislation and ordinances and reach code, you have to achieve that, and that's how you wind up getting the performance that you were looking for going through it. So click forward if you would. You begin early, and this is setting the goals and things, and you have goals around the envelope, the efficiency, waste management, materials, toxicity, obviously embodied carbon. There's all kinds of goals that you can put into place. And we have a bunch of great certification programs now, so you can kind of treat it like a buffet. When you get that group together that we saw in the sandbox, and you're talking about what do we want this building to do, it's like going through the buffet line and picking the things that you think are important as you do go through and you do it. And that can get you evidence-based performance. So if you use your existing toolkits, you can select the best fit elements of each as you go on forward. Here you see typically Passive House and Reset Air wind up being your air quality and your envelope things, but there are things on there for materials and the toxicity and accountability for the performance, social equity. There's all sorts of other things. And if you click forward in, please, for example, this is an owner's project requirement document, an OPR, and they have decided, one more click, they've decided that Passive House, the sustainability programs that they're going to get certified in are Passive House, Fitwell, which is about the experience of the people inside, and Reset Air, which is about air quality. One more click. And you put them all up here. When you get to other things in terms of your indoor environment and the materials, that's the toxicity and the embodied carbon and things. You get LEED and WELL come in, and so you can have this approach. And the important thing about it is you decided up front exactly what you wanted the building or buildings to do, how you want them to perform, and then you tracked that, modeled it, and went through, and you selected things that are very quantifiable and how to get to it. So with a 2-page document like this that gives all of your engineers where we're going, and they were a part of pulling it together, instead of having to interpret what was meant by the 4.5-page section on X, you got a number you have to achieve or a set of parameters that have to be met. So it's much, much more positive, and you do wind up getting with really good planning packages like the PHPP from Passive House or WUFI from Passive House US, we can really know what it's going to do, and literally it will perform that way. So what can you do? This is kind of the marching orders part, or the things that you could possibly do as you go forward. When we started off, we said our planet is burning and the policies are changing to address that. And whether you see this as an opportunity where you're knowing about high performance will make you a positive differentiator and grow your business, or as a threat where you better learn about it so you don't find up behind the 8 ball going forward, it doesn't matter. It is coming. It is what's going to happen. So I said earlier that our objective is to put you in a position where you're informed enough that you can decide where and how you fit. We have some suggestions for you, starting with the steps to success on the next page. This was some research that was done on Vancouver and Brussels and New York and other places where the codes are moving forward, and they're having the success and driving down the greenhouse gases in the business or of the buildings. And there are the 6 steps, but the 2 key ones that I think I'd like to highlight are to educate everyone and do pilot projects. So in terms of education, first you've got to educate yourself. The light bulb, by the way, in this drawing, the only lit light bulb in that is the one in the middle, and yet the bulbs around it are picking up the enthusiasm, the incandescence. So you stay informed and keep learning, keep going to those webinars, getting smarter like you're doing today, and then you can spread the word. If you have a business that has a website or a jurisdiction that has a website, have information on it that helps people learn about it. Have event calendars of things and places where people can go. Set up your own events to help people to do it. Those are ways to move forward. Click. And on the pilot projects, when people experience things, they get it. When you were up in the mountains of some time and you looked up at the sky and you realized that there are 10,000 times as many stars as you could see looking up from your neighborhood because of the street lights and the ambient light and things, the pilot project, when people go into a building with the right envelope and the right air quality and the lack of noise and the things, when it's built as well as it can be built, they do it. And this can be with new buildings or retrofits, and they can be already underway or on the horizon. Of course, the further out they are, the better off we are at being able to get them there, but you can do it all. I also want to emphasize top down and bottom up. If you're here and you're a CEO, you can do these things and make your company do them, or your organization. If you're a newbie that just got hired, but you're here today and learning, you can spread the word up. You can work with it to define and implement a values-based business practice. And that includes not just high performance, social equity and the things we should be doing. You can provide knowledge and skills. You can inspire others to be committed to it. And then let's celebrate success and reward effort as we go through. Those are the things that make them work forward. In jurisdictions, you can do things to incentivize high performance projects. There are some that don't cost anything, like fast tracking the planning and building process. The home I showed you earlier that was built out of the prefab components, they got approval and assembled it and put the envelope together before the windows could get there that they ordered. So they move fast. So fast track it through the process, adjust requirements and allowances for the ratio, the floor ratio, the height, the parking, the coverage. There are other things you can do that have a financial impact, like waiving or reducing fees, or causing or penalizing people that don't go all electric, or things like such as that. Provide money to promote it. You've got buildings that are owned by the jurisdiction. Could they be brought up to speed to be better and more effective? And then finally, all of you can add your voice in support. And as Ann said, there's a huge amount of change going on. There's a huge amount of opportunities for you to get involved or to stand on the sidelines and applaud. You can support policies, programs, incentives, and projects, and get involved and build toward that progress. Now that you know better, I love this duck running away from us. Now that you know better, Maya Angelou's quote of "do the best you can until you know better. Then when you know better, do better." You'll get a copy of these slides that we're using today. They have links on them, and there's things there, so you can use those hopefully going forward. Click. There's also some resources, and again, you can click on the 5 to the left. The Power of Existing Buildings is a book that was written by the people that came up with the concept of evidence-based performance that I discussed briefly. And you can go to your local bookstore or online. You will have no trouble finding that book if you're interested. So one more click to say thank you from me for your time, attention, and the fact that you're here and the commitment to doing it. And I'll pass it back to Ann.
Yes, my thanks as well. And, beg your forgiveness for getting you up to almost the 1:30 clock point. And we've told Ian that we'll be happy to stay on for a few minutes to take some questions for those of you who are able to stay. And if you're not able to, by all means, feel free to reach out to us via email. We'll be happy to correspond with you.
And Ian, I know you have to jump in 5 minutes, but if you want to make me the host, I can stay on longer and we can keep answering questions longer than that. Or I can anyway. I think Ann is available for a few more minutes too.
Absolutely.
But do you have questions for us, Ian?
No, I think that was great. I mean, a ton to unpack. We have a few questions that came in earlier. I'll just run through them. So regarding peak demand, some work is going into predicting outdoor and indoor thermal conditions for the short term and preparing the building and occupants in advance. How much can pre-cooling help reduce peak demand and cost, and maybe avoid the cost of batteries for a while?
That's a great question. And I don't think we have an answer for you, because that would take some definitely take some modeling to answer. But it's a very good reminder that pre-cooling is an excellent strategy. So we don't just use passive measures for to take advantage of solar heat, but we can do a lot of work with being, again, smarter about how we utilize the systems in the house and take use of solar energy to run your air conditioner maybe early when that energy is cheap if you have solar, and then let the house coast later when the peak is climbing.
I definitely agree with that. And I would like to go back just for a moment to phase change material. If you don't know what that is, just a big, quick, or an easy explanation is it takes X amount of power to heat water from 32 degrees where it becomes water and isn't frozen Fahrenheit to 212 degrees. That's X amount of energy to heat it that much. It takes 7x more energy to turn it into steam, to have water go to steam. That's a phase change. So a phase change materials can be set to want to be 70 degrees. And when the temperature gets that material down to 70 degrees, it will stay at 70 degrees while it gets hard as it turns into a solid. And then the same thing with the 70 degrees going back up. That's a little like pre-cooling because it's like a thermal flywheel, and it's being used in ag a lot and a bunch of places. And we're going to see more of it going forward because you can have the set point at any temperature that you need.
All right, regarding external shading, especially seasonal, is a key passive strategy. Trees have limited shading ability and take too long to grow. How can we do a better job on shading?
Well, I think the first response is to really be very judicious in placement of glazing on east and west. Also to be really aware of how solar angles during our swing seasons, spring and fall, it's easy to think, oh, summer's when it's hot, but this is California and we can get very high temperatures in spring and especially fall as well, when sun angles are lower and at a different position in the sky. So just having that awareness of the solar geometry is hugely important to window placement, and also choice of window properties. So yeah, I mean, you're right. I mean, we can't rely exclusively on trees and shading. So we need to be looking at other strategies, and window decisions are again, the first line of defense as part of the enclosure design in terms of managing the solar gains. Secondly, if we keep most of our glazing on the south, we can utilize overhangs most effectively on the south as compared to east, west, or north. On east and west facades, and to deal with some of those swing seasons, we can also look at different types of shading devices, such as vertical fins, some screening type materials that you're seeing on some of the particularly advanced commercial and some multifamily buildings. So I would say go out there and look for the award-winning, like Coat Top 10 building examples that show some of the more progressive shading strategies.
Excellent. All right, last one. Good cross ventilation is also a great passive strategy, especially for nighttime cooling and when air quality is good. Is this a good strategy for the Tri-County area?
Well, I don't live in the Tri-County area, but I think your climate is not dissimilar to where I am in Sonoma County, fairly close to the coast. So I would say yes, but I'll share a quick anecdote. Early in my indoctrination into the world of building science, I was exposed to Joe Seberg, who's one of the luminaries in this field, who was very adamant about the need for mechanical ventilation. I thought, well, yeah, but ventilation, fresh air ventilation with windows works just fine in a lot of places. But then as my education progressed, I realized, well, that's true if you live in a place where the air quality is good, you have no noise issues, you have no security, crime issues, and you're not near a freeway. There are all kinds of factors. And single family homes, it's a lot easier to achieve cross ventilation in many rooms than it is, say, in a multifamily apartment, because in multifamily, you may only have a window on one side of a room. So, and I thought, well, how many people live in those very privileged conditions? Not that many, right? Was very privileged to live in a place where I was not concerned about noise, air quality, security, or any of those issues. So I think, and of course, temperature extremes is another one. So I think that it's important to sort of run through that list in considering whether fresh air ventilation using windows is going to be effective in that location for those people with their lifestyles across the life of the building, or whether you also need filtered mechanical fresh air, and considering the source of the air as well. So, you know, we need to make sure those windows don't open where someone's going to fire up a vehicle with dirty exhaust. So a lot of considerations to factor in.
Yes, I agree, and the key is balanced ventilation in my view. Title 24 requires mechanical ventilation on any building now, but it's possible to achieve it by installing bathroom fans that run 24/7. So they do, in fact, they are always depressurizing the house, so the air is coming in. So you are getting new air, but it may or may not be fresh air. It's very likely coming from places that you would not like to have the air from. So the balanced ventilation is an important factor. So in terms of that mechanical ventilation, go with the balance. And if you want to add heat recovery to it, that's excellent as well. And when it's not too hot, cold, polleny, windy, or noisy, the cross ventilation is terrific, but being able to control it, particularly with the smoke from wildfires and things, is much superior, particularly for people in like multifamily or people who are already compromised in one way or another.
Awesome. One more trickled in, and we'll do this quick one, and then I'll buzz through my closing slides. So this person started using one-click life cycle analysis to calculate embodied carbon. Do you have a recommendation for a more comprehensive program for calculating embodied carbon? Like, for instance, how do you calculate embodied carbon in wood?
That's tricky. What I will say about this is there are a whole lot more tools out there for addressing embodied carbon and general sort of life cycle assessment than there were a few years ago. That's a rapidly evolving field. What I would do is refer you to the Embodied Carbon Network, which is housed within the University of Washington, and you can find them on the web. And they've got a whole catalog of all the LCA and embodied carbon tools, and can help you find which is going to be the best fit for your particular design problem. Carbon and wood, you know, I mean, there's a whole lot of specificity on where the wood comes from, under what sort of regime it is grown and harvested. So there's no single answer to those questions, but there are the tools that can help you.
Awesome. Thank you. Yeah, I'll just run through my closing slides and then we can wrap things up. You can advance one more. Thank you. So just quickly, a brief overview of the three programs that 3CREN currently has on offer. Next slide, please. We have the Energy Code Connect program, also known as ECC, serving all building professionals. We offer services for everyone from plans examiners and inspectors to architects and contractors for both residential and non-residential application. Under ECC, we offer three distinct services. We have trainings and quarterly regional forums covering policy and technical issues relevant to California Energy Code. And then we have the Energy Code Coach, which is an over-the-phone, online, over-the-counter, and in-the-field Title 24 consultation service meant to help building professionals navigate the California Energy Code. If you do have any, if you're involved in any projects where you have any questions on Title 24 Part 6 or Part 11, there is an inquiry form on our website. You can also call the Energy Code Coach number here on the screen. And soon in the next few weeks, you'll be able to text this Code Coach number and receive a response back within 2 hours on a standard business day. Next slide, please. So building performance training, the training we're sitting in here today falls under the BPT program. BPT serves current and prospective building professionals with trainings offered to architects, engineers, contractors, and real estate professionals. We offer expert instruction covering technical skills related to building science principles and systems for high performance buildings, as well as soft skills trainings such as sales, marketing, and communication techniques in order to grow your business or advance your career. Through BPT and ECC, we provide professional education credits, and we also have offered certifications like the NAR Green Designation and the Passive House Design Consultant Certificate. Next slide, please. Home energy savings. Lastly, HES serves households that are historically underserved, including residents whose primary language is not English, as well as low-income households, rural communities, and renters. HES offers flexible options with simple upgrades like LED light bulbs, smart thermostats, and power strips, all available for free, and then discounted upgrades that provide greater savings like heat pump water heaters, Energy Star appliances, air sealing, new windows, and insulation. And then there's no cost technical assistance available during your project. So we just launched our multifamily program about a month and a half ago, and we'll soon launch our single family program in this coming year. There is an inquiry form if you're a multifamily building owner and you're interested in finding out a bit more about the program. There's an inquiry form on our website. I encourage you to check it out. Next slide, please. So just in closing, we did have AIA Health, Safety, and Welfare learning units available for today. If you have any questions regarding that or forgot to include your AIA number in registration, feel free to reach out to me directly and I can get that sorted out for you. As Jay mentioned earlier, we will have the slides, a recording, and a survey to you later this week. We love to hear feedback from you guys, so I always encourage you to fill out the survey. We're always looking for program feedback as well as training topics that you would like us to host. We are currently working on our 2022 Q1 scheduling, so you'll likely hear from us shortly with a list of courses. But to round out the year, we have All Electric Homes 101 on Thursday this week. And then December 2nd, we have Efficient Yields Tri-County, Greenhouse Optimization. It is a course series put on by Resource Innovation Institute for cannabis cultivators. Next slide, please. So we are at time. If there are any outstanding questions, I urge you to reach out to either Jay or Ann or myself. We also have our generic info@3cren.org email here that you're welcome to reach out to as well. Thank you guys all for joining us this afternoon, and Ann and Jay for an awesome workshop. We can leave it there and enjoy the rest of your day.
Thanks
Ian.
everybody.
Thanks, Ann.
Thanks, Ian. Bye.